This is lecture number 18 for engineering statics over sections 6.1 through 6.3. And this is the first time we're going to start analyzing simple trusses. And we're going to learn about the method of joints and how to calculate forces in the members of a simple truss. And as you can see, there's a picture there of a bridge. But here's some more examples of trusses. So trusses are commonly used in support for bridges and for roofs. So when we look at the geometry of trusses, what's important is trying to figure out how much load can it handle and what are the internal forces and external forces that it is experiencing. Here's some more examples of trusses being used in different ways. We'd be looking at maybe how could we manufacture to meet load and safety requirements but still be a good budget amount. So let's start with talking about what a truss is, which we've talked about truss before is because you built your bridges. So you know that a truss is a structure that is made of slender members joined together at their end points. And we know our members, each of the different pieces of the truss, this is a member, this is a member, these are all different members of the truss. So member is just the different parts. So if a truss with its loads lies in a single plane, then it is called a planar truss. So when we start talking about simple trusses, a simple truss, which is what we're going to be analyzing, is a planar truss, which begins with a triangular element you can see off to the right here. And it can be expanded by adding two members and a joint. Two members and a joint. So where each of the members meet, we call a joint. So when we're thinking about our trusses, when designing both the member and the joints of a truss, we have to first determine the forces in each truss member. This is called the force analysis of a truss. And when doing this, we make two assumptions. Our number one assumption is that all loads are applied at the joints. So we don't have any loads in between joints. We do sometimes consider the weight of truss members, but when we're talking about simple trusses, we usually neglect the weight. So you're not going to see us including forces for the gravity, the weight. Number two is the members are joined together by smooth pins, which we learned all about in chapter 5. Are joined together by smooth pins. So this happens in real life when the joints are formed because we bolt the ends together. So that's a real life assumption that is typically safe to make. So when these two assumptions happen, the members act as two force members, which we've talked about before. They are loaded in either tension or compression. Remember, tension is pulling out, compression is squishing in, as shown over here on the right. Often, compressive members are made thicker to prevent buckling. So it's important to know whether they are in tension or compression. All right, go on to our second page. So we are going to introduce this time what is called the method of joints. So when using the method of joints to solve for all the forces in truss members, we look at the equilibrium of a joint pin. All forces acting at the joint are shown in a free body diagram. So we're going to do lots of free body diagrams for our joints. This will include all external forces as well as the forces acting in the members. So we are going to use our equations of equilibrium, specifically the sum of the forces in x equals 0 and the sum of the forces in y equals 0. We cannot use moment equations because we're only looking at a single point. So you're going to see when we draw our free body diagrams, there's nothing to take moments about. So we only work with the sum of the forces in the x and the sum of the forces in the y equals 0. And that's what we use to solve for the unknown forces acting at the joints. So I have this truss member here that's got 3 members. And it's got a rocker on one side and a smooth pin on the left side. So first what we're going to do for the method of joints is we are going to look at a joint. So let's start with joint B, because right now I'm not going to solve for the reaction forces. You could, but if I look at B, I don't have to. So let's start at B. So I'm going to say that I am drawing the free body diagram of the joint at B. You've got to label what you're doing. And then we're going to draw our axes, which we're just going to have an X and a Y. And then I'm going to draw all the forces that I see acting at B. So remember, we're using the joint as if it was a smooth pin. So I have a 500 Newton force going to the right. I have a force from A to B going straight down. So I'm going to say I have FAB. And then I have a force from B to C going off at an angle. So I'm going to call that FBC. And by looking at the triangle, we can tell that it's got a side of 2 and this side is 2. So this side is going to be the square root of 2 squared plus 2 squared, which is the square root of 8. So I'm going to write the square root of 8. So we can use that for our similar triangles. So now I'm just going to use the equilibrium equations to solve for FAB and FBC. As you can see, I only have 2 equations, so I can only solve for 2 unknowns at each joint. So let's start with some of the forces in the x direction. The reason I'm doing x first is because if I do y, I'm going to have the unknown part of FAB and a part of FBC. But if I do just the forces in the x, I'm going to be able to just solve for FBC. So I'm going to have 500 newtons going to the right, and then I have also in the positive direction FBC, and its similar triangle is going to be 2 over the square root of 8, which equals 0. Now, something I haven't said, but I'm going to talk about more in a little bit, is you always assume that members are in tension when we make our assumptions. So all of the members are going to go away from the joint when we make our assumptions. If they end up being negative, then they're in compression. So we're going to assume one way so that we can solve for the other way. So if I solve this equation, I am going to get a negative answer. which means that FBC is actually in compression. And my assumption in tension was not correct. So I'm going to get 707.1068 newtons. And now that I have that, I can sum the more forces in the y direction and solve for FAB. So let's do that. So if I sum the forces in the y direction equals 0, I'm going to have FAB going down, so negative FAB. And I also show FBC going down. Now note, I'm going to say minus, but I have the amount, the magnitude for FAB, and it's negative. So I'm going to use that negative. I'm going to say it's negative 707.1068 times its similar triangle, which is 2 over the square root of 8 equals 0. So that is actually going to turn into a positive number, which means we assumed correctly for FAB, and it is going to be in tension. So FAB equals 500 newtons. All right, we still have one member that we haven't solved for. So we've solved for FBC, check. We've solved for FAB. Now we need to solve for FAC or CA. So I am going to draw a free body diagram at point C. Now notice I didn't solve for the reaction forces. So when I draw this, I'm going to have a reaction of C in the y direction from that rocker. And I'm not going to solve for it this time, even though I could, because I can do 2 unknowns at each intersection. But I'm going to draw my axes. We've got CY going up because it's a rocker, so it only has an upward force. To the left, I have FAC. Remember, I'm assuming that it is in tension. And I also have going to the left and up, I have FBC, which I know, and it is negative 707.1068. All right, so now if I solve for my forces in the x direction, I'm going to be able to find FAC. Oops, I forgot to note that this similar triangle for FBC is 2 square root of 8. So if I sum my forces in the x direction equals 0, I'm going to have negative FAC, and I also have negative FBC, which is negative 707.1068, and its similar triangle is 2 over the square root of 8, and that equals 0. So now I can solve for FAC, which is going to be positive, so it is in tension, and it equals 500 newtons. So now I've got all of my answers, but I need to write the information out as my solutions. So what I'm going to do now is I'm going to draw my solutions. I'm going to write them out and box them so it's obvious what they are. So first we solve for FBC, and it is 707.11 newtons, and it is negative, so it is going to be in compression. So we're going to put a C. We solve for FAB, and we got 500 newtons, and it was positive, so it is in tension. We also solved for FAC, which was also equal to 500 newtons, and it was positive, so it is also in tension. So this is how I would express my answers, and I will box them so they can be easily seen. All right, we've got a little bit more to talk about before we go on and do another problem. So let's talk a little bit more about the method of joints process. So when we're looking at the method of joints process, what we're going to do is we're going to start with the joints. With one or two unknown forces. We can't solve more than two because we only have two equations. With one or two unknown forces. So that's the first thing we're going to do, is look for joints where we only have one or two unknown forces. If we don't have that, then we're going to have to draw a free body diagram of the entire truss and determine the support reactions. So it's typical that we are going to determine the support reactions. We just didn't have to on the last one. The second thing we're going to do is what we just did, and we're going to draw the free body diagram of the joint. And we're going to assume all the unknown member forces act in tension. So the force is going away from the joint. Then we are going to apply the scalar equations of equilibrium. Which are sum of the forces in the x equals 0 and the sum of the forces in the y equals 0. Remember, we can't use moments because we're only looking at a single point, so we don't have any distances. And remember, if the answer is positive, then our assumed direction tension is correct. Otherwise, it's in the opposite direction and it's in compression. Then we're going to just repeat those steps. Repeat steps 2 and 3 until we solve for all the forces we're looking for at each joint. One thing to note is you may have zero force members. And it's good to knock those out early so you don't spend your time solving for them. So let's talk about what they are. If a joint has only two members at it, and there's no external load or support reaction at those joints, then those two members are zero force members. So in this example to my right, see we have this joint here at A. If I was to draw the free body diagram of A, I would end up seeing that I have a force going up and I have a force going to the right. Well, if I solve for those by equilibrium, I'm going to get that they are both equal to 0 because there are no other forces acting on them, so they have to be 0. So, in other words, AB equals 0 and AF equals 0. Similarly, if I look over here at D, I'm going to notice that if I was to draw a free body diagram for D, I'm going to have one force going down, and I'm going to have the other force off at an angle. Now, the reason that this is a zero force member is because this force going off at an angle has an x component. But since we don't have any other x forces, it's got to be 0, which makes the one going down, FDC, also equal to 0. So both of these are equal to 0. So if you are solving these, you need to notice which ones equal 0 so you don't spend your time trying to figure out what they are. So this picture down below just shows what the truss is going to look like if we were going to analyze it without those zero force members. So it would just shows the joints and which members we would need to consider. So this is our zero force members are removed. I'll just note that so you know. All right, let's look at at another example now that we've gone through a little more formally and talked about zero force members. Let's look at our next example. So in example number 2, we are going to determine the force in each member of the truss shown, and we're going to talk about whether they are in tension or compression. Now you notice looking at this, at all of the joints, I either have an external force like I do here at D, or I have support reactions like I do at C. At B, I have an external force, and at A, I'm going to have a support reaction. So there are no joints looking at this that only are going to have 2 forces acting on them, because at A, I'm going to have an upward force from the rocker, and at B, I'm going to have an X and a Y force as a result of the pin. So I'm going to need to take the free body diagram and solve for the support reactions for this truss. So I've already taken the time to draw over here what the picture looks like for my free body diagram of the whole truss as an entire body. So I'm going to draw on it my forces, because this is my free body diagram for the entire truss. So I've got the 400 Newton force going straight down at B. At C, I've got a force in the X direction. You can assume it to be positive or negative. That's up to you. I'm going to assume positive. I'm also going to assume the X component, because it is a joint, a smooth pin. So we've got an X component. And then I have a 600 Newton force down here at the bottom right. And then I've got the force just straight up from a rocker. Because the rocker force can only go in one direction, it has to go straight up. I'm going to call that A of Y. There is no X component on the rocker because it's not keeping me from moving in the X direction. So the first thing I'm going to do is use my equilibrium equations that I know to solve for A of Y, C of Y, and C of X. Now I can use the moment equation in this example because I have distances between my forces, whereas at a point we don't. We're just looking at a point. So I am going to use that, because if I solve an X or Y, well, I could solve an X first and I would be able to solve for C of X, but with C of Y and A of Y, I'm not going to be able to solve for those unless I use a moment equation. So I'm going to use the moment equation where I have the most forces, and that's the point I'm going to choose. So I'm going to say that my counterclockwise is positive, and I'm going to sum the moments about C. Since there are 2 forces there that I don't know, I'm going to choose that as my joint. So I'm going to have from C, I'm going to have the 400 Newton force, which is acting counterclockwise, so it's positive 400 at a distance of 3 meters. And then I've got A of Y acting clockwise, which is negative, and it is at a distance of 6 meters. And then I have the 600 newtons, which is pushing me counterclockwise, so it's positive, and its distance is 4 meters, equals 0. And my answer, when I solve for that, I'm going to get that A of Y equals 600 newtons. And I assumed up, since it's positive, that means my assumption was correct, so A of Y is 600 newtons in the upward direction. So now let's do our forces in the X direction. So plus, we're going to assume to the right is positive. The sum of our forces in the X direction equals 0. And so I've only got 2 forces. I've got C of X, which I assumed positive, and then I've got a positive 600, and that equals 0, which means that C of X equals negative 600 newtons, so I assumed the direction wrong. So that means it is 600 newtons going to the left. All right, my last equation, is to sum my forces in the Y direction. Equals 0. And in my Y direction, I've got A of y, which I don't know yet. Oh no, I do know A of y, whoops. I've got A of y, which I know is 600 newtons going up, so it's plus 600 newtons. I've got the 400 newtons going down, minus 400. I've got C of y that I assumed to be up, so plus C of y. And that's all I have in the y direction, equals 0. So with that, I can solve for C of y, and I get that C of y equals negative 200 newtons. So I assumed that wrong as well, which means it is going to be 200 newtons going down. All right, now we can do our analysis at our joints. So we want to start with the joint where we only have one or two unknown forces. So we could start with A because we have one known force and two unknowns. So right now that's probably our best one to start with. So let's do our free body diagram. So I'm going to label that I'm doing it at A. And I'm going to draw my axis. So I've got my Y, I've got my X. All right, let's look at what we've got. So we've got A of Y, which is going up because we assumed that correct, and that is 600 newtons. I've got FAD going off to the right. So FAD going straight off to the right, and then going up and to the right, I have FAB, and I'm going to draw its similar little triangle, which I've got the information for on the labeled truss. So its similar triangle is going to be a 3 in the X. Oh, that was bad. Can't really see that. A 3, a 4 in the Y, which means that the hypotenuse is going to be 5. So now we have our two equilibrium equations we can use to solve for FAD and FAB. I'm going to first solve for FAB because I can do the Y components and solve for it by itself. If I tried to solve for the X components, I have two unknowns, so I wouldn't be able to solve them yet. So let's do, in the positive upward direction, sum of the forces in the Y equals 0. And I've got my 600 going up plus my FAB, and its upward component is 4 over 5. That's all I have in the Y direction. And notice that I drew all of my forces going away from the joint because I'm assuming they're in tension. If I get them in negative, that means they're in compression. But we're assuming that they're in tension to start. So when I solve this equation, I am going to get that FAB is negative. So it is indeed in compression. It is negative 750 newtons. All right, now we can do our sum of the forces in the X direction. So I'm going to assume to the right is positive. Sum of the forces in X equals 0. So I've got FAD in positive, and then I assumed that FAB was positive, but it's really negative. So I'm going to put plus the negative 750, and its X component is 3 over 5 equals 0, which means when I solve for FAD, it is going to be positive, so it is in tension, and it is 450 newtons. All right, so I've solved for 2. So we can check off that we have gotten FAB, check, and FAD, check. So now if I look at where I should go next, I can go 2 places. I could go to B, there's only 2 unknowns there now, or I could go to D. So I'm going to select going to B, just because that's what I decided to do on my paper, but you can select to go to D, and that is fine as well. So let's draw our free body diagram at B. So at B, I'm going to label that it's at B. I'm going to draw my X and Y axis. And then I've got, acting at that joint, I've got a force acting straight down of 400 newtons. I've got a force to the right that I don't know yet. That's FBC. And I'm going to assume it's in tension, so we're assuming it's away. And we know FAB, so I'm going to draw FAB over here, and we know what that is. And even though I drew it in tension, so I'm going to show that it is negative 750. And I'm going to do the similar triangle for that, which is 3, 4, and 5. And then I've got one more force going from B to D in this direction, down and to the right, FBD. And its similar triangle is going to be also 3, 4, and 5. 3, 4, 5 triangle. So looking at my forces, I am going to solve first in the Y direction because then I can solve for FBD. If I try to go in the X direction, I'm going to get two unknowns because I don't know FBC or FBD. So let's do in the Y direction first. So I'm going to say plus up is positive. Sum of the forces in the Y equals 0. So I'm going to say I have negative 400. I also have FAB, which is negative, because I assumed it negative, but it is also negative, so it is going to end up being positive. You are welcome to draw it the other way if it doesn't confuse you. I just like to keep the numbers the same. So I'm going to have negative 750 times its Y component is 4 over 5. And then I'm going to have a negative FBD, I assumed it was in tension, times 4 over 5 as well, equals 0. So I can now solve for FBD, and I get the FBD equals 250 newtons. So it is positive, it's in tension. So now that I know FBD, I can do the sum of the forces in the X direction, equals 0. And I can say I know that FAB, I assumed negative, but it is negative also. So negative 750 times 3 over 5. Then I have FBC, which I assumed positive, so it's going to be plus FBC. And FBD, I also assumed positive. And it is positive, so we're going to put plus 250 times 3 over 5 equals 0. So if I solve for FBC, I'm going to get a negative number. I get negative 600 newtons. So it is in compression. So I have now solved for 2 more, so I have 1 more to solve for. I analyzed FBD and FBC, so what I have left is FCD. So we can use the joint at C. I'm going to choose the joint at C because I think it's the easiest just looking at it, but you could also do at D. That would work as well. You only have one unknown at D now also. I'm going to use C. All right, I'm going to draw my X and Y axis. And acting at C, I have, from what I solved for C of Y, and it was downwards. So it was a down 200 newtons, so I have a downward 200 newton. And I also had an X component of C, which when we solve for that was also negative. So it is going to be going this way, 600 newtons. All right, those were my support reaction forces. Now I'm going to draw my forces that are coming, that I have calculated. So I have FBC, which I've calculated to be negative 600 newtons. So I'm going to draw it as if it was in tension, but it is negative 600 FBC. So like I said, you could draw it the other way and show that it's negative already. And then I've got going down, I've got FCD. So FCD is the only one I don't know. That's what I'm going to solve for. So I'm going to use the forces in the y direction because it is in the y direction. And I'm going to assume upwards is positive. And I've got negative 200 going down from my support reaction. And I assumed negative FCD because it's in tension. But this is going to show me that FCD is going to end up being negative then, so it is actually in compression. So now that I have all of them, I'm going to write them out, and I'm going to list all of them so that I have them in one place so my teacher could find them really easily. All right, so I have FAB equals 750 newtons in compression. I have FAD equals 450 newtons in tension. Notice I don't need to do the reactions, the support reactions, because I wasn't asked to do that. I was only asked to do the members, so I'm not going to solve for them. I have FBD equals 250 newtons, and it was positive, so it is in tension. And I have FBC, which was in compression because it was negative, so it's going to be 600 newtons in compression. And I have one more, FCD, it's my last one, and that equals 200 newtons, and it was negative, so it is also in compression. And I'm going to put a nice little box around it so my teacher sees it. All right, there is one more example problem in the notes, but I'm going to do it in a separate video. You're welcome to watch that or go on and take the quiz and do the homework.